Good morning, sir. This is Jaffney of Computer Science Engineering Department. My concept is about backtracking. Introduction to backtracking. Backtracking is an algorithm technique for the problem solving and incrementally. It involves the building candidates for the solutions and abandoning them if they fail to satisfy the constraints. This method is particularly useful for solving the combinational problems and the puzzles. Historical context. The concept of the backtracking has the roots in a mathematical logic and computer science. Early algorithms were developed in the 1950s to solve problems such as the n-queens problems. Over time, backtracking has evolved and been adapted for the various applications, including the AI and optimizations. How backtracking works. Backtracking explores the all possible configurations to find a solution. It systematically builds the candidates and tests them against the problem's constraints. If a candidate fails, backtracks to the last valid state and tries the next options. Key concepts of the backtracking. The search space defines all possible solutions to the problem being solved. The decisions of the tree represents the choices made at each step of the algorithms. Constraints are the rules that must be satisfied for the solutions to be valid. Applications of the backtracking. Backtracking is commonly used in solving puzzles like the Sudoku and the crosswords. It can also be applied in the optimizations of problems such as the traveling and the salesman problems. Backtracking is the concept commonly used in solving the puzzles. Additionally, backtracking is also utilized in the artificial intelligence, and it is also used for path finding and in the game theory. Backtracking versus the brute force. Backtracking is more efficient than the brute force as it avoids the exploring the invalid paths, while brute force examines the every possible solutions. Backtracking spawns the search space. Backtracking is the more efficient than brute force. This results in the significant of the time savings and also results in the large problems, especially with many constraints. Backtracking algorithms. Common backtracking of the algorithms includes the depth first search space and the n-queues of the algorithms. These algorithms are designed to systematically explore and backtracking as the necessary. Implementing these algorithms requires a clear understanding of the problem constraints. Complexity of the backtracking. The time complexity of the backtracking algorithm can vary significantly based on the algorithm's problems. In the worst case, the complexity can be exponential, particularly in large search spaces. However, effective pruning can dramatically reduce the average case complexity. The time complexity of the backtracking algorithms can vary significantly based on the problems. Challenges in backtracking. Backtracking can become inefficient if not implemented with a proper heuristics. The challenge lies in defining constraints that effectively reduce the search space. Additionally, managing the memory and also recursion depth is crucial for the large problems. Conclusion on future directions on backtracking. Backtracking remains a crucial technique in the algorithms design and the problem solvings. Future developments may focus on the hybrid approaches, combining the backtracking with the algorithms. As computational power increases, backtracking's applicability to the larger and more problems will grow. Thank you, sir.